Welcome back to our channel Prash. Learning is fun. In this module, I am going to explain about circular motion. Do you know a giant wheel? It is one of the major attractions of the carnival. It consists of a rotating upright wheel with multiple passenger cabins. Each cabin is attached to the center of the rim. The wheel tends to move along a fixed circular path. These cabins are equidistant from the center. So, we say that movement of a giant wheel is circulatory. The path followed by each cabin is circular because all the cabins are equidistant from the fixed point, that is from the center. So, we say that a giant wheel is an example of circulatory motion. So, if a particle is moving along a circular path, then the particle is said to be in circular motion. So, let us see some examples of circular motion. Planets revolving around the sun is a prominent example for circular motion in real life. These planets tend to follow a fixed circular orbit that acts as a boundary of the circle, while the sun acts as the center of the circular path. Orbiting around the planet. The movement of satellites around the planet is exhibited in a fixed orbit that is usually circular in nature. Another example for circular motion is stone tied to its string. When a string is attached to a stone and one end is supplied with some force, it will swirl in air. The stone rises to a height and traces a circular path. A special kind of force known as centripetal force acts on the stone, and that helps in maintaining the circular motion. So regarding centripetal force, we are going to learn in this video. Circular motion can be either uniform or non-uniform. So uniform circular motion and non-uniform circular motion. When can we say that a particle is in uniform circular motion? We can say that a particle is in uniform circular motion when speed is constant. So when speed is constant, we call it as uniform circular motion. And when the speed is not constant, we call it as non-uniform circular motion. Consider a particle moving with a constant speed of 5 meters per second in a circular path. So here the particle is moving with a speed of 5 meters per second. Here speed is constant. That means it is in uniform circular motion. Then what about its velocity? Is velocity constant? We can say that velocity is constant in magnitude. But what about its direction? Let us see what is the direction of this particle at this point. So the direction of the particle at this point will be tangent drawn at that point. So this will be the direction of the velocity. Now let us consider another point here. Now let us see the velocity direction here. So velocity direction will be tangent drawn at this point. So here, if we observe at each and every point when the particle is moving in a circle, each and every point, the direction of velocity is changing continuously. Since velocity is changing continuously, this particle possesses some acceleration. So this acceleration is called as centripetal acceleration. Let us derive an expression for centripetal acceleration. Consider an object moving in a circular path of radius r with an angular displacement of theta. Let the velocity at this position is v1 and the velocity at this position is v2. Now, let us draw a vector triangle involving v1 and v2. So, this is v1 and v2. What does this side of the triangle represent? This represents delta v, that is nothing but change in velocity. The original velocity and change in velocity, this is change in velocity, will give you the final velocity. Here the angle made is theta. So this is the same angle as we got here. R and R forms an angle theta. Similarly, V1 and V2 forms an angle theta because here R and V1 are perpendicular to each other. Similarly, R and V2 are perpendicular to each other. Now, I will draw another triangle with R and R. So, this is one R and R. This angle will be of course theta. Then what should be this side of the triangle correspond to? Now look here. This is the arc length. This arc length should be exactly equal to V delta t. V delta t. Here delta t is the amount of time taken by the object to move from here to here. And V is the speed. And here V1 is equal to V2 because we are taking it as a constant speed. The arc length is V delta t. If theta is very small, then arc length will be same as the length of line joining these 2 points. The curvy arc length and the straight line joining these 2 points are practically same if theta is very small. So, the third side of the triangle will be V delta t. So, we are deriving the instantaneous acceleration, then the angular displacement will be very small. So, when the theta is very small, then we say that this arc length will be equal to the line joining these 2 points. If we observe these two triangles are similar triangles because they both are isosceles triangle subtended by an angle of theta. So for similar triangles, the corresponding sides are equal. So we can write it as delta V by V. Here V1 is equal to V2. V1 is equal to V2 is equal to V. So delta V by V is equal to V delta T by R. V delta T by R. So I will rewrite this equation delta V by delta T. I am bringing delta T to this side is equal to V into V. So we will get V square by R. So delta V by delta T is nothing but instantaneous acceleration. So AN is equal to V square by R. So this is the required equation. So when a body is moving in a uniform circular motion, then the acceleration produced is centripetal acceleration. That acceleration is equal to V square by R. Magnitude of acceleration is given by V square by R. Then what about its direction? Here the direction of acceleration lies along the radius towards the center at every instant. So this direction we call it as a radial direction, which always acts inward direction and is equal to the normal for a circle. So at every point the direction of acceleration is changing. It means that acceleration is not uniform even though speed is constant. So in uniform circular motion, speed remains constant but velocity changes continuously. And acceleration also changes continuously. So, to maintain a particle in a uniform circular motion, a force should act. This force is called as centripetal force. Define centripetal force as the resultant force along the normal direction which is directed towards the center is called as centripetal force. From Newton's second law, we know that force is equal to mass into acceleration. Here Fc is equal to mass into V square by R. Here V square by R is an instantaneous acceleration, that is centripetal acceleration, that is equal to V square by R. So resultant force Fc is equal to m into V square by R. So this is the formula to find the centripetal force. To describe a particle in translative motion, we use linear kinematic quantities like distance, displacement, velocity and acceleration. And to describe a particle in circular motion, we use angular kinematic quantities such as angular position, angular displacement, angular velocity and angular acceleration. So let us see one by one. Consider a particle P moving in a circular path of center O. Let O be the origin and OX the x-axis. So join OX, x-axis. So to describe the position of the particle, we have to draw a line joining OP such that OPOX makes an angle θ1. So the angular position of point P will be θ1. If we consider another point Q, So join QO, which is making an angle theta 2. So now position of particle P, angular position of particle P will be angular position of particle P is theta 1. Similarly, angular position of particle Q is theta 2. Now let us check out what is angular displacement. When a particle P is moved from point P to Q, then its angular position changes from theta 1 to theta 2. That means when the change in angular position is called as angular displacement. Angular displacement is indicated with the letter delta theta. So delta theta is equal to change in the angular position is called as angular displacement. So angular displacement delta theta is equal to theta 2 minus theta 1. So here SI unit will be radian. Since this angle made is a plane angle. So we know that plane angle is a supplementary quantity. So it has no dimensions. So during one complete revolution, the particle makes an angular displacement of 2 pi radians. So one revolution, we call it as one revolution is equal to 2 pi radians, that is equal to 360 degrees. What will be the angular velocity of this particle? If the angular position of the particle is changing from theta 1 to theta 2 from time t1 to t2, let us consider that at point P time is t1, at point Q time is t2. So now delta theta is equal to theta 2 minus theta 1. This is the angular displacement, and change in time will be t2 minus t1. So now let us write the formula for average angular velocity. The average angular velocity can be described as angular displacement per unit time. Okay, so now change in angular position is theta 2 is delta theta is equal to theta 2 minus theta 1, and delta t is equal to t2 minus t1. So now angular velocity we indicate with the letter omega. So omega average is equal to delta theta by delta t, that is equal to theta 2 minus theta 1 by t2 minus t1. The SI units will be radian per seconds. So dimension formula will be t power minus 1. Since there are no dimensions for radian, we will get only t power minus 1. Now moving to the instantaneous average velocity. What do you mean by instantaneous average velocity? Instantaneous angular velocity at a particular instant is given by instantaneous angular velocity. That means angular velocity at a particular instant of time. So to check out to know the angular velocity, instantaneous angular velocity, omega is equal to limit t tends to 0 delta theta by delta t is equal to d theta by dt. So by using this formula, we can find the instantaneous angular velocity. So we have already studied about SI units, that is radian per second. This angular velocity is measured in revolutions per minute. So 1 revolution per minute is equal to 2 pi by 60. So we can write it as pi by 30 radian per second. We will also use revolutions per second. So that is equal to 2 pi by 1, that is equal to 2 pi radian per seconds. Or theta radians. Theta radian is equal to theta by 2 pi revolutions. So SI units of angular velocity is radian per second. But most often angular velocity is also measured in revolutions per minute and revolutions per second. So 1 revolution per minute is equal to 2 pi by 60. That means 1 revolution per minute. 1 minute is equal to 60 seconds. So 2 pi by 60. That is equal to pi by 30 radian per second. And we also measure in revolutions per second. 1 revolution per second is equal to 2 pi by 1 second. That is equal to 2 pi radian per seconds. Now theta radian is equal to theta by 2 pi revolutions. Now let us see what is the time taken by the particle to complete one revolution. So the time period of a particle can be described as the time taken by a particle to complete one revolution along a circular path. So we know that time is equal to distance by speed. So distance traveled by a particle to complete one revolution is 2 pi, and time taken is speed is equal to omega. Speed is equal to omega. So let us write the relation. T is equal to 2 pi by omega. From here we can write it as omega is equal to 2 pi by T. So this is the relation between time period and omega. Omega is nothing but the average angular velocity. So moving to angular acceleration, change in angular velocity per unit time is called as angular acceleration. Suppose if the angular velocity changes from omega 1 to omega 2 in time t, then angular acceleration alpha is given by omega 2 minus omega 1 by t. So let us write the SI units. So SI units are radian per second square, and dimensional formula will be given by t power minus 2. So average angular velocity will be given by average angular velocity is given by omega 1 plus omega 2 by 2. When a particle is moving in a circle, two important things we need to discuss. One is the radial direction. Radial direction coincides with the normal direction in case of a circle. So this is equal to AN along the normal. And this direction we call it as tangential direction. It is drawn at a point on a circle, AT. So these two are perpendicular to each other. So when these two are perpendicular to each other, this line joining these 2 points will give you the resultant acceleration, that is equal to AN. So the resultant acceleration will be A. So A is equal to root over, from Pythagoras theorem we will get AN square plus AT square. So this is the resultant acceleration. If AT is equal to 0, then what happens? Then A is equal to root over AN square. So which implies A is equal to AN. So this is the condition when the particle is moving in a uniform circular motion. So if a particle is moving in uniform circular motion, AT is equal to 0. When AT is equal to 0, A is equal to AN. That means the particle will have only radial acceleration. If AT is not equal to 0 and AN is also not equal to 0, then what happens? A is equal to root over AN square plus AT square. So this is the condition when the particle is moving in a non-uniform circular motion. So in non-uniform circular motion, AT is not equal to 0, AN is also not equal to 0. So resultant acceleration will be root over AN square plus AT square. That means the body possesses both tangential acceleration and radial acceleration. Now what happens if AN is equal to 0 and AT also equal to 0? When these both are equal, then resultant acceleration A also will be equal to 0. That means the particle is moving with a uniform velocity in a straight line. So when a particle is moving along a straight line with uniform velocity, then AN is equal to 0 and AT also equal to 0. That means the body does not possess either radial acceleration or tangential acceleration. So resultant acceleration will be equal to 0. So we know that when a resultant acceleration is 0, then the particle may move with uniform velocity. If a particle is moving along a straight line with increasing velocity, then what happens? When the particle is moving with increasing velocity, AN is equal to 0 and AT not equal to 0. That means body possesses only, the resultant acceleration will be only AT. That means the particle is moving in a straight line with increasing velocity since AT is not equal to 0. So now let us differentiate between uniform circular motion and non-uniform circular motion. In uniform circular motion, speed remains constant. And in non-uniform circular motion, speed is not constant. Though speed is constant, here velocity changes continuously. So here velocity is not constant. Here also velocity is not constant, since speed is not constant. When it comes to uniform circular motion, angular velocity remains constant. Angular velocity remains constant. But here angular velocity is not constant. And since velocity is not constant, acceleration is not constant. Here also acceleration is not constant. Since angular velocity remains constant, angular acceleration will be equal to 0. Angular acceleration is 0. So here angular acceleration is not equal to 0. So it is understood that in uniform circular motion, speed remains constant, angular velocity remains constant, and angular acceleration is equal to 0. Since angular acceleration is 0, we can write the equations of motion. Since angular acceleration is constant in uniform circular motion, we can write the equations of motion. So first let us write the equations of motion for linear motion. For linear motion, final velocity is equal to initial velocity plus acceleration into time. That is equal to v is equal to u plus at. And s is equal to ut plus half at squared. So here s is the displacement. And v square minus u square is equal to 2as. So these are the three equations of motion. And finally we know that Sn is equal to u plus a by 2 into 2n minus 1. This is the nth second. So let us replace these with angular kinematics. So final velocity, initial velocity u will be replaced as omega 1, and final velocity v is replaced with omega 2. Acceleration is replaced with angular acceleration alpha, and displacement is replaced with theta, and t is equal to t. So I will rewrite the equations now. So equations for angular kinematics will be equal to omega 2 is equal to omega 1 plus alpha into t, and second one theta is equal to omega 1 t plus half into alpha t square, and omega 2 square minus omega 1 square is equal to 2 alpha theta, and finally nth second theta n is equal to omega n plus alpha by 2 into 2n minus 1. So these are the equations for angular kinematics. So the resultant acceleration is equal to a is equal to root over an square plus at square. So now let us find out the relations and the formulas for an and at. So before going to that, first let us find out the relation between linear velocity and angular velocity. So if a particle is moving in a circle with a radius r, then this is the angle this is the angle theta, and the angular displacement will be s. S is the arc length here. So arc length is equal to arc length is equal to s, that is equal to r theta. So on differentiating, I will get ds by dt. With respect to time, I am differentiating. So d by dt of r theta. Here r is the radius of the circle, so r is constant. So we will get ds by dt is equal to r into d theta by dt. And we know that ds by dt is nothing but change in displacement by time. Change in displacement by time is nothing but the linear velocity v is equal to r dot d theta by dt is nothing but change in angular velocity, angular displacement by time. So angular displacement by time is equal to omega. So we know that, so the relation between linear and angular velocity is v is equal to r omega. Now coming to the normal acceleration is equal to normal acceleration is equal to an. So an is equal to, we already know that the particle is moving in a circle. The particle is moving in a circle, then the radial acceleration coincides with the normal acceleration. So that is equal to this normal acceleration will be equal to the centripetal acceleration, that is nothing but v square by r. So I am substituting the value of v here. So r square omega square by r. So r gets cancelled, so we'll get r omega square. This can be further written as an is equal to r omega. Say this I can write as r into omega. So we know that r omega is equal to v, so v omega. So an is equal to v omega. This is the normal acceleration. So relation between tangential acceleration and angular acceleration. So at is the tangential acceleration. We know the tangential acceleration is equal to change in velocity by time. So dv by dt. So we know that v is equal to r omega. So I write d by dt of r into omega. So I can write as, since r is a constant, I will write it as d omega by dt. So r dot d omega by dt is nothing but alpha. This is the angular acceleration. So finally I will get that tangential acceleration is equal to r into alpha. In the next video, we are going to discuss about the circular turnings and banking of rods. So keep watching Prash. Thank you.